Imagine a choice you make tomorrow, reaching back in time to change an event that already happened yesterday. In physics, this concept is known as retrocausality, the idea that the future can overwrite the past. This starts with the baseline rule of the quantum world. When a subatomic particle travels unobserved, it behaves like a rippling wave. But the moment you measure its physical path, it behaves like a solid pebble. Physicist Niels Bohr called this the principle of complementarity. He argued that a particle can exhibit wave-like behavior or particle-like behavior, but it is physically impossible to observe both at the same time. This setup tests the limits of chronological ordering. If a measurement made after a particle has already landed can determine how it behaved in flight, then the standard sequence of cause and effect no longer holds. In this version of the double-slit experiment, every particle that passes through the slits is entangled with a secondary path marker. This marker acts as a physical record of which slit the particle chose. The primary particle completes its journey and hits the final detection screen on a Monday. Meanwhile, the path marker is isolated and stored, effectively freezing the record of its journey until the timer reaches Friday. On Friday, the experimenter faces two options. They can read the marker to see the path, or they can perform a separate measurement that effectively erases that information. When the path information is destroyed on Friday, the Monday data reveals overlapping bands of light and dark, the signature of wave interference. However, if the marker is read, those Monday impacts remain a random, unstructured scatter. The interference disappears. This creates a powerful illusion. It appears that hitting an erase button today rewrites the physics of an event that was finalized several days ago. To understand the resolution, we have to rethink the detection screen. Instead of a flat wall, imagine the screen as a discrete row of buckets, each numbered 1 through 10. When the particle behaves like a wave, its two possible paths interfere. The waves constructively align to force the particle into the odd-numbered slots, while destructively canceling out over the even-numbered buckets. Conversely, if the particle acts like a solid pebble, there is no wave interference. It simply travels through one slit and has an equal probability of landing in any bucket across the entire row. The fundamental insight is that the screen is actually a measuring device. The moment a specific bucket registers an impact, the universe has performed a physical measurement. Because the particle and marker are entangled, they share a single quantum state. Hitting a specific bucket on Monday instantly forces the distant marker into a corresponding fixed state. This is the immediate consequence of measuring one half of an entangled pair. By the time Friday arrives, the experimenter has no actual control over the marker. The specific bucket the particle chose on Monday has already dictated the marker's state. The physical arrival at the bucket permanently locks the path information into a scrambled or coherent state. The past is settled before the experimenter even approaches the lab. This chart shows the data points from the odd-numbered buckets. When these are isolated, they form a clean, distinct wave crest pattern. When we add the data from the even-numbered buckets, a second wave pattern appears on the same axis. Notice that these waves are perfectly inverted. The peaks of the even bucket wave land exactly where the valleys of the odd bucket wave occur. When you view all the particles together, these two waves cancel each other out. The result is a flat, featureless distribution that hides the interference entirely. The phenomenon of quantum erasure relies on sorting this unstructured beta set into coherent groups. Extracting these hidden waves is a matter of correct categorization rather than altering historical events. In a real lab, scientists work with continuous detection screens rather than discrete buckets. This makes extracting these phase-shifted waves an incredibly complex mathematical task, as the bucket size effectively shrinks to a single point. This core mechanic, where measurement causes an instant collapse of quantum information, is the fundamental cornerstone of modern quantum cryptography. Because measuring an entangled particle instantly fixes its partner's state, any attempt to intercept a secure communication beam automatically scrambles the wave, providing an immediate warning of a hacker's presence. The final screen serves as the definitive measurement. It projects the entangled system into a fixed state the millisecond the particle lands, long before any delayed choice can be made. The laws of causality are secure. The future remains strictly ahead, and yesterday's history is locked away the very moment it happens.